Welcome back to the deep dive. Okay, if you've ever felt, completely bogged down by huge, complex data sets. Well, today we're talking about a kind of mathematical cheat code, eigenvalues and eigenvectors. That's right. Our mission really is to show you how these concepts basically unlock the hidden structure inside matrices. It's like finding the secret operating system. And it gives you this massive shortcut to computational power.
Yeah, and we're digging into the source material here to focus on, well, two main things. First, the geometry. What do real eigenvectors really tell us visually? And second, how does understanding that geometry help us, slash the complexity when we're doing heavy matrix calculations, like finding high powers of a matrix? Okay, let's break that down then. If you think of a matrix as doing something to space, like stretching it or rotating it,
well, geometrically speaking, they're kind of like the stable pathways.
Why these vectors?
Imagine stretching space. Most vectors get pulled off their original direction. They twist and turn. Right. But the eigenvectors, they're the special ones. They stay exactly on their original line. Their length might change. They might get stretched or shrunk. But their direction doesn't budge. It's invariant. Invariant. Okay, that quality, that's huge. It sounds like they're speaking the matrix's own internal language.
They absolutely are. Yeah. The eigenvalue that goes with each eigenvector, that tells you precisely how much scaling happens along that direction. Ah, okay. And this isn't just abstract math on a page. Think about population models like Leslie matrices, the biggest eigenvalue. That single number can predict the whole population's long-term future.
Really? How so?
Well, if that value is bigger than 1, the population, it grows exponentially forever. If it's less than 1, eventually it dies out. It collapses. That one number holds the key.
Wow. Okay. That really connects the theory to, well, actual prediction. Predictive science. So let's take that idea, that invariant quality, and bring it over to the computation side.
Calculating things like polynomials of matrices, or say $1 to the power of 100 for some big matrix dollar. That sounds like a nightmare. What's the shortcut here?
The shortcut is, well, it's pretty neat. We use the structure of these eigenvectors to essentially translate hard matrix multiplication into simple arithmetic. If a matrix dollars is diagonalizable, meaning it has enough independent eigenvectors, we can rewrite it. We express it using a matrix of its eigenvectors, let's call it Q dollar, and a diagonal matrix containing its eigenvalues. We call that lambda. The formula is $1 of Q lambda Q1. That's the decomposition.
Okay, I think I followed the decomposition at 1Q lambda Q1, but hang on, why does writing $1 that way make calculating A1 easier?
Because when you need to calculate $1 to some power, say A1, that formula simplifies beautifully. It becomes Q times lambda times Q1. Yeah, and here's the magic. Since lambda is diagonal, just numbers along the main diagonal, zeros everywhere else, calculating lambda is a trivial. You just take each individual eigenvalue on the diagonal lambda and raise it to the power. Oh, I see. So instead of multiplying the whole matrix Ryer by itself 100 times.
Exactly. Instead of, say, 100 really messy computationally expensive matrix multiplications, you're just doing 100 simple scalar exponentiation, just raising numbers to a power. That's an incredible simplification. Huge. It makes really complex problems solvable. It's the difference between a calculation taking seconds versus, potentially years or just crashing the computer entirely.
Yeah, I can see how that would be incredibly empowering, especially if you're a student or researcher facing these massive systems. Okay, but to use this power, you need the tools, right? like MATLAB using commands like A to get the eigenvalues and eigenvectors. That's the practical skill you need. But there's a catch, isn't there? I remember seeing something about potential pitfalls. Right, VDIA in MATLAB gives you the eigenvector matrix Eulers and the diagonal eigenvalue matrix Eulers.
Definitely. And this is where critical thinking comes in. You run the command, but you have to interpret the output carefully. Sometimes, because of how computers handle numbers, the results look messy.
Messy how?
Like you might expect a nice clean integer eigenvalue maybe 3, but MATLAB might give you something like 3.00000000000 plus some tiny imaginary part like 1015, just numerical noise.
Okay, so you need to know enough math to say okay, that's basically 3.
Exactly. Or you might deal with a rotation matrix. Its eigenvalues can be complex numbers, which makes perfect sense geometrically, but you need to understand why. And then there are these tricky defective matrices.
Defective? What does that mean?
It means they don't have enough linearly independent eigenvectors to form that Kittel matrix properly. They aren't diagonalizable in the simple way we just discussed.
So what happens if you run Eigen on one of those?
Well, the software will still give you something, but it might not be the clean diagonal matrix lambda you were hoping for. It might give you a related form, like the Jordan normal form, or the output might just look strange. You need the underlying mathematical knowledge to recognize what's happening and why the standard diagonalization doesn't quite work.
Right. So the lesson is the software is a powerful tool, but it's not a magic wand.
You can't just blindly trust the output. Precisely. The real mastery isn't just running the command. It's understanding the math well enough to know if the output makes sense, what its limitations are, and how to interpret it correctly, especially when things get weird.
So summing up, eigenvectors give us this invariant viewpoint. It reveals the fundamental directions of a transformation, and that clarity not only simplifies massive computations, but also forces you, the learner, to be a sharper critical thinker about the tools you're using.
Absolutely. And maybe a final thought for you to take away. Getting your head around concepts like Eigen decomposition isn't just about passing a math course. It really hands you a set of universal keys. Keys to unlock incredibly complex problems, whether in physics, engineering, data science, even biology.
A universal key?
Yeah. So think about it. What really complex system are you working on or studying?
Could there be a hidden simplification waiting? Could you find its invariant direction, its eigenvectors, and unlock a whole new level of understanding? Go look for them.